Greetings, dear readers, earthlings. Reading Foundations today with Ross Finlayson, myself. This August 15, a great day every year. It will be titled something like From Quine to Scott, From Fresnel to FitzGerald. And so what that's about, to begin, is that Quine, Willard Van Orman Quine, is considered one of the greater technical philosophers of the 20th century. And Dana Scott is considered one of the better logicians of the 20th century. So Quine is present in the surrounds of Carnap and the Vienna School and the formalism, as it were, of logicist positivism as the way of things. In the time of Derrida and Husserl, and Husserl's meditations on geometry, but matters of sense, and for reading of Kant, and the basic account that Kant is seminal or original in the so being that the rational Enlightenment saw that the synthetic tradition more than less, and here there's an analytic synthetic distinction and an analytic synthetic contradistinction, and a analytic synthetic inverse in a sense. What is in accords just from reason, the analytic, what is made or stipulated, the synthetic, or vice versa. That Kant is given the account of reviving, recycling the works of the Epicureans and so on, the sophists of the more ancient times. And then having it so that as well, he reserves in his vocabulary for his discussion the noumenon for the phenomenon, that of the mental senses, as they would be, the mental faculties. And then for the sublime and the ding-an-sich, the accounts of the extraordinary for things like infinity and the empty set and so on. So Quine then was in the circle of Carnap, and for example, Tarski, Alfred Tarski, Teitelbaum, is originally his name was before he changed it to Tarski, to avoid persecution in the time of World War II and such times. That Quine is a logician, and he hails from the area of Boston, say. He's a Bostonian, from what I understand. And so Quine, he studied logic after Russell, and Russell and Whitehead in the Principia Mathematica. And he's a powerful formalist with the ability to make so clear in a readout of abstract symbolism, the formalism, the formulas, to make for so that he has in his works, for example, his book Set Theory, or and later in other accounts, but in Set Theory, Quine's book Set Theory, he writes a set theory and also breaks down what goes into making Russell's and Whitehead's set theory in their account, and relating it to Principia Mathematica and the accounts of well, is equals a primary or primitive relation in the theory? Yeah, well, for Russell, it's no. And it's like, well, what about x not in x and vis-a-vis x in x? Which one of those is disallowed when the other one would have via ready comprehension the derivation of a contradiction? And so Quine in set theory, and it's been read here quite some time ago, in Logos 2000, or that account of reading from Quine, or in this reading foundations from reading from Quine, more of word and object vis-a-vis set theory. The set theory was earlier in Quine's career, and so it's a scholastic, studious reading of set theory in a formulaic setting. And then Quine introduces, for examples, about how to formalize the reals first before the rationals, the complete order field before the rationals. So there's a way to make it, when it accounts of what must be a class and what can be a set in a set theory, where you'd figure they'd be the same because it's only a theory of one relation. There can't really be anything else in it. Then any mention of a class at all in the context of set theory makes it set theory with classes. That otherwise a set is defined by its members, and the relation of a member to its set is elt, B elt A, B the element is an elt or element of A. And the other one is contains, that A contains B, the class A contains the element B. And the reflexive sorts of relations, and you'd figure that they would just be the same, but there are some ways to define things that are classes and not being able to individuate, a word Quine uses, their elements. And similarly, there's a way to consider elements composed together, the collections, the gesammelt, the collected participle together, that can't make sets anymore. So Quine introduces that there are various ways to go about picking what makes for tracks up this sort of logical mountain, and shows and demonstrates, for example, alternative ways to arrive at the rationals from the reals instead of the reals from rationals. So whether the reals are a class, they don't exist in the set theory of this ordinary, or the rationals are a class, they're only derived or stipulated to exist, are these sorts of accounts that make for reasons why, when in the thorough sort of reading of the diligence of the rigor of the mathematical logic, that these various sorts of accounts keep it so that Russell's way, for example, is not the only way, and then that there are others is also then, well, they all have to live together too. And so how that's accomplished, in a sense, is here's an account of the extraordinary. Since the ordinary, after Russell's retro-thesis, which is that anybody knows that quantification over sets can, and the set of all sets that don't contain themselves, which is the very rule that's given then for well-foundedness. Nothing contains itself in its transitive closure, it's ordinary. There's everything's got an minimal element, or there's no infinite descending epsilon chains or ELT chains. The idea of the usual count of that reality, and here that's considered more in that Logos 2000 Rulial Foundations. It's explained quite thoroughly for an hour or so. Has it that, then besides accounts of the extraordinary, which Quine also does get to a little bit later, then also he just picks apart the various components that come in and go out of it. So what Quine gets into later in set theory, his book, is the class set distinction. And so it's for Quine what are named proper classes. Although in his book he calls them ultimate classes. So ultimate classes are classes that are not sets. They just can't be sets because it would be paradoxical to have them be built from sets, yet at the same time they're classes and forms of relation. So in the reading here from Russell in Principia Mathematica and the Philosophy of Mathematics, Russell also kind of is pained to mention that the class set distinction is where he said he'd often have things he'd much rather write as class comprehension schema than as sets, but he can't because it violates a rule he's made for himself and must tacitly utter every single time he says anything else at all, a restriction of comprehension, in having made a definition of what a set is when it's ordinary in that sense. So Russell wasn't ignorant of these issues, but he wasn't very upfront with these issues when it came to then claiming the completeness and the other sorts of guarantees of the theory about the terms that Russell uses, like isolation and significance, and turning those over and what it means when a restriction of comprehension is or is not significant in its isolation, these sorts of accounts. So Quine then in his account of atoms, which would be like the elements. It's like, well, these are elements and we can't decompose them, but they must be composed of something because everything's composed of something. We'll call them atoms, say. And then these ultimate classes, though, are more so with regards to things like the universal class. It's like, is there a relation of everything at all? It's like, is usually the account. And that's for like a first class account of equality and identity and tautology. I'll have it that the class set distinction then has so that the decisions and opinions made in the early definitions of what a set is have that the opposite sort of opinions arise to fill the context of the theory, and to have it so that what results is the ability to describe things that would naturally occur due to comprehension and the expansion of comprehension, like a universal set or an ordinal of all ordinals, that being like infinity. It would contain itself. It would be greater than itself. It's sublime, as Kant would put it, mathematically. Whereas Kant's account of the sublime was more of the infinite and the absolute vis-a-vis a mathematical logic, Kant. And then, though, that Kant gets into decision and judgment and these sorts of accounts for reason and reason's sake. So Quine has these as kind of a couple of his signposts of things that are superclassical or extraordinary. That otherwise, Quine very firmly sits in the camp of conservative. And by that, what he means is that the entire argument from authority and for correspondent and coherent and pragmatist theories of truth is that he frames quite usually his large course otherwise, or at least from the essays I've seen of him and the books I've read from him. Only with some few remarkable exceptions, like these ultimate classes, about what it means to have a class comprehension schema as a universal account. Terms from logic, as they may be given. So Quine then has this other account of something extraordinary that I thought to mention, because otherwise it's just the great strength of rational thought, and then early in his career, and then as he developed, then getting into word and object, and then into his later career, where as a more famous sort of figure, then he ended up talking a lot more about the meaning and epistemology and the accounts of semiotics, as they would be, although I'm not sure if he ever quite used that phrase. Yet the accounts of the looser talk in philosophy and the accommodation of the intersubjective, a word that Quine uses, as at least since the 1970s. And here it's generally given that all the words, except words I make up like theory and so on, have their meaning in the literature, if not since forever, in the 20th century, quite thoroughly. That Quine gets then into word and object. So here there's an account of things like the laws of large numbers, and as they would be, or the models of continuous domains, and how after the extraordinary account in the superclassical, that there are these the replete settings to be established instead of the merely complete. For the weak induction, there's a strong induction account, and then for the replete, that the analytical bridges keep them together instead of contradictory, and these sorts of things, and so on. So Quine, from the notion of being a bit more reticent or hesitant, or simply as of his opinion or his understanding, to stay inside the theory, has more like levels of like modal relativism or the relevance. And so in word and object, one of the what came to me as like one of the most telling things about it was that he'd say, at some point in time, Russell's isolation, meaning his kind of purity and form of his structure, is not so relevant anymore. And so what becomes when the weak and the strong change hands, or when the rulil and the counter rulil change hands or cross these bridges in a sense, symmetry-flex, which is a word I made up, instead of symmetry breaking, which is for invariant theory, which is impossible according to invariant theory. That the possible is these accounts of the analytical bridges that so hold, or in the analytische Brücken, which is just analytical bridges in German, the same words. How's it that Quine, as part of his account of not being later just called having no concept of these things, like the extraordinary set theory, the anti-foundational, and these and that, has it that he does at least have a scaffold or a stairwell or what's the word, a fire escape, as it would be, like when a building has a stairwell on the outside in case of a fire that he could get out. And so that's the notion then of that being just kind of at the top of his theory, Quine's. It has that it's also just kind of on the side of his theory. And so it can't really be said that he'd have been ignorant of matters of the paradoxes of induction and quantification and identity and continuity and infinity. And he was very familiar with the formal construction by all the possible considered means of the integers, the rationals, the reals, and so on, the objects of geometry, according to Hardy's account of equating geometry and numbers, and for Hilbert and the like, and the whole idea since Descartes and so on, which is after the Muslim Enlightenment and these kinds of things, for the algebra and analysis upon the objects of arithmetic and geometry, for algebraizations of arithmetic and geometry, arithmetizations, geometrizations, the model theory. Quine thusly has, as this is accommodating, that there are these pluralities. And usually I'd avoid saying plurality because it's used in the language today to mean two different theories that disagree but saying they don't, and just acting like they don't. And it's also called fragmentism or being fragmented. And so, but pluralism, when there are plural laws of large numbers and plural domains, what that has done is taken what's a singularity and establishing that it's a branch in a multiplicity theory. So in mathematics, these terms, openings, perestroikas, catastrophes, mean, for example, that the positive numbers happen to have negative factors, because minus times minus equals plus. Whereas in a world of only positive numbers, one might say, this is like, that's impossible. There's no such thing as a negative number. And this is a usual idea since antiquity and magnitudes and so on. Can't count backwards. You have to change direction and count the other way or something like that. So it's an opening and a perestroika and a catastrophe in the theory of positive numbers, that there aren't negative factors. It's similar with complex numbers. It's similar with complex numbers and left-right division, another opening that is ignored in the usual accounts of complex analysis, which many thought kind of, especially as they started kind of seaming and stitching around the edges, thinking that it kind of closed the loop, as it were, about the complete ordered field, that the complex numbers have this whole other sort of account due the non-uniqueness of division, and the distinctness then of it, the branches in the multiplicity theory. So Quine at least then has these examples of relevance and so on, and they're plural or they're hierarchical. Here the plural accounts are either hierarchical, like the larger and largest laws of large numbers, to making for inductive limits, and then infinite limits truly, and continuum limits even more strongly, and as after superclassical results like Zeno's Archer and Zeno's moving rows, or the graduation course, as it put it, wind sprinters, making for doubling spaces and doubling measures and halving spaces and halving measures. This then has that Quine in word and object much more further explores and begins to establish that language is its own space. So this was talked about in this Quine language space in that Logos 2000, I believe it was, and it's about Quine's work and relating it to the development and the maturation of a philosopher and a logician into what he found to be compelling to him. So there's one other thing I want to mention about Quine is this, is that here there's a usual ready example of the apple in the universe and everything that it is not. And so this is a matter, and it's used to, for example, to consider and to define identity. So I was watching this interview or panel with Quine recorded 30, 40 years ago on the YouTube, on one of the many channels that have Quine's essays. And so the Quine example of with Brian Magee in the Brian Magee and the Contemporary Philosophers, you can find that on that Musitorium playlist about 4 hours in. There's an episode with Quine and Magee. But then there's another episode, for example, with Goldfarb, who's the chair of philosophy at Harvard or something like that. And Quine is an emeritus from Harvard University, considered one of the premier programs for most things. But in the accounts of philosophy and logic here, that the notion of the apple in the universe is what Quine calls a cosmic complement. So he got to talking about class comprehension schema, and is usually won't say anything about the extraordinary at all. But one of the interviewers prompted him to describe something. At first, he started talking about classes and classes ad infinitum. So what he was talking about, things at all, things in the real universe, and what they are, and what their identity is. And so he started talking about classes of classes and so on, or class comprehension schema. And then he got to talking about that. Well, the whole universe of things is made up of these things. It's a thing. It's all one universe, and so on and so forth. And then with that, he got to talking about the cosmic complement is what he put it. So from Quine we get ultimate classes or proper classes, and cosmic complement or identity. And so in his course of describing these things, and particularly he's used the word individuation, which in one sense is just establishing what an individual is. And another kind of stronger sense is like, what is an individual in an infinity of individuals? Or what is the individual in a continuum of individuals? Usually individua are the constituents of continua, the idea being. And there's an integer continuum before the line rails, and a long line continuum after the signal rails here. For the three continuous domains, and then accounts of how those come from the integer continuum since Duns Scotus and Spinoza, and the long line continuum of Dubois-Reymond, a great thinker in the account of infinity, and an original thinker in the 19th century. Habitat, and then besides whether, for example, it's ready to show that given the development of the rationals and the development of the line reals, that one or the other of them is necessarily a class to the other one being a set, and these sorts of things, class set distinction, has it so. Then the Quine with the cosmic complement is considered, that's the first sort of account. I don't think I made up myself, the idea of the apple in the universe. And so that would be something that would be part of Quine's less conservative or extraordinary detail, and it goes to show that otherwise he wouldn't have said so much. But those are some things he said, and they're to be held for Quine as being sort of original or originating from him. And then the account that the schools so related will eventually have matters of understanding, revisiting and understanding what that is, and not just inventing a new one. Like, for example, the accounts of, well, add more large cardinals. Well, they're not cardinals. They're not sets. They would just be contradictory. Well, they're plural were the fragments. You know, you've got at least two theories there. This is all one theory, is the idea. And so these are considered kind of Quine's important contributions. Like if Einstein had the cosmological constant and mass energy equivalency, his important contributions to the concept. These are what I would consider for Quine. It'd be the ultimate classes, or proper classes, ultimate classes, and the cosmic complement. Not the complement to make a statement that's complementary that is deemed positive or do praise or something like that. But the complementary, like complementary duals, they complete each other these ways. So it's kind of completion and in the extraordinary. And so here then that goes well with it, though the universe set minus an object is also the elementary embedding of the model of the universe into the model of the empty. And so for things like Quine inconsistency, which otherwise is given as kind of like, well, it's the end of set theory before there's no universe anyways. But on the way up the cumulative hierarchy, which is just transcendental ordinals higher and higher and higher, usually ordinals, the cumulative hierarchy, and it counts as models of sets and ordinals, because ordinals and sets come from two different theories. They're fundamental theory where they're elements in primary piece, the ordering theory and the set theory. These are among the accounts then of why this episode would be titled Quine to begin. Something about Quine. And I didn't really find another good episode to add to the musitorium, but there are bits and pieces in them. Because otherwise then, getting into examples like the Two Dogmas of Empiricism, so this was written somewhat later and it was considered kind of a gauntlet thrown down to logicist positivism and people who claim guarantees from finite approximations, which are unfounded. And so without becoming too non-conservative, say, and definitely not non-classical, which is another way of saying fragmented pluralism usually, when non-standard just means extraordinary. Quine in the Two Dogmas of Empiricism then kind of comes up with a third one, and so that's just more of his accounts of the modal relativism in a sense. And it gives them kind of like his own insulation from otherwise people who get it wrong, but that said is still in the box in a sense. So that said, it's at least got one thing about it that knows what's in the box and knows it's in the box and these kinds of things. Thinking inside the box. So then this next fellow is Dana Scott. And I found in his musitorium an account in his later years that Scott was a logician, and he was at the Berkeley School in the time of Tarski in the School of Logic. So that was considered the kind of the premier center of this. And there was like a school out of Chicago, and there's a school out of Pennsylvania, and some other accounts of schools of logic in the United States in the 50s and 60s and 70s. So Dana Scott sat with like Solomon Pfefferman, Tarski, and that's pretty much who comes to mind in that what's called Berkeley School. Because I'm not a fan of Montague, who's said to give an account of like, well, if we can say it in symbolic logic, we can say it in natural language. I got Herbrand for that, Herbrand semantics. And then for Tarski, in the usual account of Tarski truth, that can be read some more from the considerations back in Logos 2000 about the cyclic metaphysic and the like. That it's an example of what's inside the theory, inside the box. And so the accounts of various reductionisms, as there would be, and Tarski was a great sort of reductionist. Then explicating detail of the forms he could so follow in this singularity he'd made of the theory. Then there's Pfefferman has quantifier disambiguation, because otherwise, if you don't have to think about the transfer principle and bridge results between these accounts of the paraconsistent and dialetheic, there's no such thing as difference between for any, for each, for every, and for all. Or much difference between exists unique, exists non-unique, or exists distinct. And otherwise, the universal and existential quantifiers of logic can be distinguished and made contradistinct to each other about the for any, the for every, the for each, and the for all. Or in a sort of ordering is like for each, for any, for every, for all. Those being stronger sorts of accounts that express the comprehension at once. So Solomon Pfefferman about impredicativity introduces the idea of quantifier disambiguation. So Scott has got a couple different tricks up his sleeve in a sense. Again, quite usually just inside the theory and having, for example, books about in the 1970s about like a model of computation or Scott's computers, say. After something like Turing, which is kind of like follow the instruction pointer, never look back, or something like that. Then the account of memory or the von Neumann architecture, that Scott would probably have something to do both with type theory and then with comprehension a number of different ways about a wider sort of account because Scott's both has he's got Scott's trick, which is like, well, it's like Skolem and Lowenheim. In fact, you could say it's just a reading of Skolem and Lowenheim with expansion and collapse. So you can take something that's countable and say there's an uncountable model of it. But furthermore, you can take something that's uncountable and say that there's a countable model of it that fully embodies all of its relations in its structure. So that's kind of what I make of that. And then I've been trying to think of it, one or a few more things that Scott has come up with. But one of them is circle and box modality. So this is basically the account for the quantifier disambiguation and the modality of like the compactness of the integers. Is there a point at infinity? Yes. Then they're compact. They have the property of compactness. Is the direct sum of infinitely many copies of the integers the empty set? By the usual definition, yes. By the definition given it by the greater surrounds of axiomatic set theory, no, because it would make a contradiction. So the accounts of these modalities then, because it's framed in the sense of a modal logic, has which one kind of is in effect, the reality of the thing. So the reason I mentioned Scott is in his discussion that he has of this this lecture he gives to a theory on the lambda calculus for some functional programming designers in a sense, or language engineers or programmers about lambdas and the lambda calculus and the like. Then Scott gives a bunch of different examples of where he'll be talking about things in one mode, like for numbers or sets or collections or relations, and then explain why when he's talking about that coming together and coming apart that there are two modes. Whereas the usual account of like the term free or the variable free or the constant free, meaning having eliminated these possibilities, is absent and bereft of that. Simply more fungible in a sense and tractable to many means, yet not really sensible when it's wrong or paints itself into the corner. So Scott has this, and that's, I think, with a co-author in Landau or something like that. I don't know so much about it, but it's Scott's idea. So in the time of like when Edward Nelson, who is a set theorist, he would study something like, well, I got internal set theory. What's that? It's like, well, it's kind of like when you're looking at the reals and want to take all you want to take all the partitions and into having open sets everywhere, and so it's almost everywhere discontinuous, but it's everywhere dense, and it's also almost everywhere dense in this internal set theory. And it's not the same as Zermelo-Fraenkel set theory or ZFC, Zermelo-Fraenkel set theory with classes. So Edward Nelson is this other guy who is popular or notable in the time of the 80s and 90s and 2000 or so, that IST is co-consistent with ZFC, meaning they don't model each other. They're not the same theory, but if one of them's consistent, then the other one's consistent, and vice versa. Neither would give to each other. So that's Nelson's usual result of the co-consistency of ZFC and IST. And I've also seen other people, like my friend DL, who in a simple college undergraduate paper wrote that they're consistent. And then also about after IST, it's usually given that accounts of mathematical infinitesimals with real analytical character are consistent. So that's not usually given to the account of the co-consistency, the consistency with respect to each other of IST, internal set theory, and ZFC, Zermelo-Fraenkel with choice. Yet that's one of the things in play of among these modes. So Scott is familiar with that, and then also he just gives lots of examples of how the theory deals with otherwise these matters of independence as they would be in the results or inconsistencies, and to at least frame them on the same page, if not in the same box. So box and circle modality, and there are some other examples from Scott that are extraordinary in this sense, or at least speak to the superclassical and so on. And then otherwise, like Scott's trick in this and like is kind of like, well, yeah, as Skolem already gave kind of the extraordinary account and showed is like, yeah, model relativism is bigger, smaller, it's infinite, it's inside outside itself naturally enough according to Skolem, and just using a double reductio and a counter induction and counter development. So. Then if quantifier disambiguation, the term is kind of out of the school, Berkeley School. And then Scott's modalities, circle and box modalities primarily, and that being about, I'd frame it in terms of the integers, but also it can be used for accounts of like the line reals vis-a-vis the field reals. Terms from here about continuous domains, which are defined by having extent, density, completeness itself without being axiomatized, given, and measure itself without being axiomatized, derived, these sorts of things. Then that's why I talk about Quine and Scott today. Then the next account, or following that, is one other mathematician that I've been curious about and want to know more about was Longlons. So Longlons is an algebraist in a sense. And so what he has to do with is the Longlons program. And I found this essay of him, or video essay, or a lecture from him. And it's on this Musitorium bit. And so what it is like a 90th birthday festschrift for a guy named Mostow, M-O-S-T-O-W, who I don't know so much about. But what it is this guy Longlons, and he gets up and he explains what the Longlons result is, and going from groups and actions on groups to matters of geometry for topology sheaves, and then how to get back from that. And so and he describes it in a sense like, well, it's coming from geometry, it's this way, and going from sheaves, it's the other way. So this is algebraic geometry. Algebra is not geometry. Geometry is not algebra. Geometry can embody pretty much anything that would usually be given as an algebra. Magmas are a looser collection of algebras. And so sometimes when you hear about algebras and people say, it's like, well, I'm going to let out the relation. It's not closed anymore. Or it's non-commutative. And it's like, well, okay, but does it come all the way back around? Or, I mean, can you switch those back and forth, whether it's an algebra or not? The reversibility and reflexivity and these sorts of things. For relation, algebra defines relations. The geometry already has them. That's the structure. It's like this is just the space and the point in the space and everything in between. It's geometry. So algebraic geometry here it belongs to geometry, not algebra. But the point of the Longlons program is then to relate. Basically, that what amused me about this was that Longlons said, people ask me what the Longlons program is. You have to ask somebody else because they've been writing about it for years and just say what they want. And from my perspective, it's this matter of the actions between the groups in geometry and back and forth. For theirs, it's usually the algebraic geometry, or the Bourbaki. Nicolas Bourbaki is a fictional character. It's a panel of a man. It's these French mathematicians who lived in France before World War II, say, and who made a school of algebra. And then that's usually given to Grothendieck, who's like, well, I got universes in my theory. I got Teichmuller universes. I got categories way up here. And then so our algebras are going to attain to that. And so modular forms, the Taniyama-Shimura way, and a lot of different things in algebraic geometry are said to be Bourbaki, and then the account of the Longlons program. And so not everybody has that's that way. Like Lefschetz and Picard and other algebraic geometers, and for that we might start with Poincaré, an algebraic geometer, has that as algebraic geometry. not algebraic geometry. So that's just a usual thing to say about Langlands, is that he's kind of on the fence on that one, and definitely so, because but he can definitely point to either side and say, algebra, you're not being geometry enough, and geometry, you're not being algebra enough when it comes to the Langlands program more widely. So from the horse's mouth, as it were, that's a good that's something I really took to heart, or thought he really meant when he was just kind of being off-putting about it. Langlands there at a little lecture at Yale 10 or 15 years ago. So that's about from Quine to Scott, say. And then in the 21st century, that's all fragmented in a lot of cases. And so due to combinatorial enumeration, so many people studying everything and always looking for something new to study, then there's lots of different logics. But Scott's account of the box and circle modality is kind of sitting there. And when people look at the greater reasonings about Nelson's internal set theory and Zermelo-Fraenkel set theory, ZFC, and their accounts and the co-consistency thereof and the independence of each other, basically, while yet in the greater surround of incompleteness of the Gödelian and the independence of the continuum hypothesis, which isn't just due Gödel, but also von Neumann next, who proved it the other way. He showed it the other way. And then Cohen stepped in and said, well, here's a third way that nobody's wrong. As that it really doesn't give an account back out of there together again. So quantifier disambiguation, though, and the modalities at least gets into the formula. Like here, the material implication is simply taboo, because it has true-false tables, and when they're neither true nor false, instead of just leaving a blank, it fills it in. Wrong. It says, oh, this will never matter because it's never so. The moon is made of green cheese, so the moon is made of green cheese. Or anything that's just not so. So it's got those gaps in it to keep it perfect. And then similarly, the quantifiers, when they're jammed together and when there's impredicativity, it's not predicative, it's impredicative. Then the quantifier disambiguation, when there are the analytical bridges for superclassical and the completion results, is necessary to have quantifier disambiguation. And then the modalities to keep it a modal logic. So it's all, a modal logic means it's all one mode. So that's the way that these things go. Then having the circle and box modalities is given this, like, all this sheet and all its formulas are like here, all this sheet and all its formulas like so. They are all in one theory. They only exchange with these bridge results called the transfer principle, which usually is given that, what's the transfer principle say? Is like what you can say about each of them is also what's so for all of them. Like each of the ordinals up to a point is also an ordinal. Each of the sets up to a set is also a set. So that's usually given to Burali-Forti about the class of all those. But the point here is that that's 21st century, and that's what there is today. So Nelson and IST, that was 20th century, late, or fin de siècle, Y2K, before Y2K, 20th century. And then Quine was a formalist, and very strong formalist, before he became more of a just a plainer sort of account of himself as not being wrong. But he does occasionally expose himself or open himself up and share his real opinion about things like the cosmic complement, and then after ultimate classes. That I would be interested in hearing what he said more about that, although his writings on these matters speak for themselves. So then that's about that 20th century logic bit. And then the 18th and 19th century physics is, and this was about Fresnel and FitzGerald. So to keep this brief then, these are parts of the counts of the F-Lorentzians, F for forces and fields, and then cataloged by easy to remember mnemonic names like Faraday, Fizeau, Fresnel, FitzGerald, Finley-Freundlich, Freundlich again, Feynman, Fatio, about accounts of general relativity and special relativity for E-Lorentzians or E-Einstein. E-energy relations. So energy is just kind of the quantity, and then fields and forces about the space in which they live. So Fresnel is then got an account for light. So Fresnel goes together with Huygens because they both give accounts of light as a wave. And here, light is distinguished as a form of radiation from electromagnetic radiation as a form of radiation. So the usual model says, oh, all our radiation is the same. They follow the same propagation. In fact, then we have the same amount of energy according to frequency and wavelength. So light and electromagnetic radiation are the same. It's like, well, they're equal about that. They're not the same. And so the account they can't. All the experiments say that they're the same. It's like, well, actually, the experiments say that light diffracts, and then the signal of electromagnetic radiation is compounded refraction. It just has echoed all the way back up and down. So here, there's an account that light is special with kind of raised in the middle, and our eyes evolved to see optical light because it's got free information flowing around and it's visible in that manner. The signal of the image is according to the decoherence and all the inputs flowing together, the freest sort of account. Since Lucretius, the ancient Roman scientist and theoretical physicist, the films of the images. So the account then that light in the middle has got a dual tri-stimulus color space and is pure diffraction instead of compounded refraction. It fits in the model and all the data already. So it's not saying they're different and there's something wrong with the experiment all these years. Instead, it points out that there's room in the theory why they're different, and all the theory why they're different. So we got Huygens principle, and it's like the usual account of Huygens principle is kind of an adiabatic account, and it's related to Lagrange. Is also this kind of simple reductionist account. But the other account of Huygens is waves make waves, and so this is that. Then there's the account of waves and wavelets, and then waves and wave spirals and spiral waves and spiralets. That being a word I made up, spiralets, I suppose. And then putting wave spiral and spiral wave together is not new by any means. Vortex or vortices, or what Descartes or Kelvin would have called them, and they have their theories where these are the primary objects in the theory. So Fresnel then is just giving an account as for light is that the occult Fresnel, for example, when experiencing something like the transit of a syzygy, like an eclipse or something like that, or even just the fact that the light is massless and chargeless and doesn't interact with electromagnetic radiation, they're different. There is electromagnetic radiation in light's range of frequency and wavelength. That's not light. So and then the accounts of like the Young's experiment. So Young is a famous. This is a proper name. He's a famous optician, like Airy, A-I-R-Y, and Young, Y-O-U-N-G. Like with the dual slit experiment after interferometry and diffraction gratings and so on. So that the beams, when vis-a-vis the screens and the electrons as beams, have that masers and lasers are different. And then that they get added up to be the same is certainly a great coincidence. I'll agree, but then to explain that it's not exactly so, that it's a perfect coincidence, there's room in the theory and room in the data, because then the reasoning experiment to show that is not so is simply enough that light doesn't interact with electromagnetic radiation to cause interference. So that given the account that light is pure diffraction and E&M radio is compounded refraction. Now, this is the idea I have here. I just made this up. Nobody else is going to give this much credence unless they hear it like this or make of their own account why these things would be so. That there's room in the theory and room in the data, room in the formalism and room in the data of the room in the theory, so that science will allow it. Then has the other point about the difference between light and radio is like, besides the propagation relations are always the same, because otherwise it's just radiation. It just radiates. So does heat. So does nuclear radiation. Different. And these kinds of things. Then has that light's image is decoherence collected together, and the radio signal's information is coherence, particularly. The decoherence causes the loss of image and signal, and the coherence in the light causes basically a loss of image of the signal. So they're two different things, opposites to each other. Like it's like saying electricity and water are the same because they both have a fluid model. They're not the same. But after energy, then the kind of radiation and propagation is very fundamental in the physics. So that's what I want to mention about Fresnel. And then FitzGerald is also about this. Because then in the account of electricity and magnetism and space contraction, there's like, well, it had to be length contraction and time dilation together. Or special relativity mostly gives accounts of time dilation and the account of length contraction. But FitzGerald was around first, and before, before Maxwell. I mean, after Faraday. But there's FitzGerald and Heaviside and Larmor saw that in the 1900s, or the 1800s of the 19th century, that Larmor and FitzGerald and Heaviside formed part of the development in Great Britain during the time of the Industrial Age, particularly like the steam engine, but all kinds of things metal. And then the development of the electrical and the great, I'm coming up with that, like Heaviside and then the telegrapher's equation. And that FitzGerald then, for the fields, he had all the potential fields that they were working on and with. So before Maxwell, he was developing the theory of electricity and charge and magnetism and static electricity and dynamic electricity or current. About the laws of Faraday, that the integral over it is one thing, and ampere is like the current through it is nothing, and Coulomb is that like, well, the skin effect is bringing electrons across for the electron theory of matter. So the static. Those three, each having three laws, then like later the Maxwell, then for Ohm and Kirchoff, besides, is like the simpler accounts just of circuits closed and the fluid model of the things. Then Maxwell also says, hey, E cross B or D cross H, take your pick about which way the electrical field lines and the magnetic field lines cross. There are two different ways. One or the other of them is fictitious or virtual to the other. And then that it's all been one way since then, and that's just called like Maxwell's laws. For James Clerk Maxwell, an excellent electrician who made a reductive account that was perfectly suitable for all kinds of things, because phase, flux, and the superclassical behavior of that electromagnetism's radiation is on both sides of the spectrum. It's got high frequency and low frequency components. And then when there's the double spectrality and these kinds of things, that and the resonance theory, usually enough about it. And for like, well, Faraday has found one line, and then Zeeman found three lines, and then Zeeman kind of dialed it back again and put it back to one line for Faraday's experiment and Zeeman's experiment about the behavior of light in electrical field and media. Which led to spectroscopies kind of being given after Rutherford, and the kind of spectroscopy is kind of being given, which is account from a lot of different things, the colors of flames, since a long time ago, about how to identify things by measures, their physical constitution, or spectroscopy, like for mass spectroscopy and all this kind of stuff, compared to nuclear magnetic resonance, which is an entirely different sort of account in resonance theory instead of spectroscopy. It goes to show then that FitzGerald is famous for space contraction. So the account of like, well, Einstein's theory has got length contraction and time dilation. It's like, yeah, that's from space contraction. And then it's like, well, Michelson Morley says that light doesn't do anything different when you spin around a turnstile on the Earth. It's like, well, yeah, it doesn't have to either. But that there is one is like the account then for Fresnel to get back into why then in that's then the wider account given back to Fresnel of, so that for dark matter and dark energy, that according to Fresnel and FitzGerald, kind of lifting what they have up and saying this is a model of the world. And Einstein might be okay with part of this, at least, because he says later, he's like, oh, yeah, ether is definitely a thing. because space exists. I mean, if you talk about space-time, you definitely got a real space everywhere. Otherwise, it's just particles in nothing. So Einstein's already got a space, and then he's working on his total, too. And then he's got reductionisms and formalism that says, these give some equations from what we can see from here. And these kinds of things. Have it that, thusly, I just want to make that as account of kind of what's in the context here is already kind of given because it's been around forever. And so then explaining why dark matter and dark energy are so measured is that for free rotating frames, it's like, well, that's just its own rotating frame. It doesn't need more mass. That it is luminous energy because the mechanics itself gets revisited. And that's discussed a lot more here in previous episodes. And many of my posts on Usenet, if howsoever brief and amidst many trolls, these kinds of things. And then, what's the account then for Fresnel? Oh, the dark energy and the light. It's like, well, how can light take so long to get here? Why does the universe look like it's expanding all the time? It's like, well, the account is like, well, when it gets here, then it goes around, the circle comes in. So this Fresnel occult lensing is like the pure diffraction brings it all around to come down and in. And then there's the account of that the light speed is actually given a reason for what its value is, also according to space contraction. It makes for Fresnel and FitzGerald a way to look and to take into account what they already said. And what are usually said is, well, these are definitely in the theory, or these are definitely not in the theory. Yet they're just so, for their own accounts. Have that they're not only so, but they bring themselves back very strongly. So, Fresnel and FitzGerald. Well, then that's the account today. I haven't quite gotten into the books yet, but that'll be next time. So next time it's books about algebraic geometry to start the stack here. Let's look at this for a while. This is a 3-volume set called Methods of Algebraic Geometry. Hodge and Pedo. Hodge and Pedoe. Methods of Algebraic Geometry from Cambridge Press. So this is book 1, marked by a little star, and this one by 2 stars, and this one by 3. The accounts of algebraic geometry has that it's like, well, it's you know how we have an analytical setting to treat geometry like by real numbers and analysis. So algebra is treating them as groups. So then we can treat them kind of like we do with numbers when we're just canceling stuff above and below the divisor bar vis-a-vis inside and outside the differential and integral. Those being kind of the methods available. It's like, well, this is when we have 2 of them together, so let's see what happens with that. Linear algebra, matrices, determinants, and linear dependence. So linear dependence is also a sort of relative account because what's linearly independent is also, in a sense, then dependent on that vector basis with regards to the metric and norm and stuff like that. Examples of fields, the division algorithm, divisors and common divisors. So this is a great account. This is a book on algebra so far. Polynomial rings, classification of rings. Here there's earlier read a great book on normed rings, which is like, well, what's a normed ring? It's like, well, you know how a ring, like, the farther away you look at it, the smaller it appears to diminish on the far end? Well, yeah, that's a matter of perspective. It's like, well, on the far end, that increment is as big as this increment. It's got a norm. Yet at the same time, it kind of trails away. So that just brings like the whole point about the circle and box modality and compactification from the logic fundamentally of what can arrive at making a structure and model of these things all the way back. Normed rings. So I got this 3-volume set at a book fair for $150. Hodge, William Dallas Douglas, Methods of Algebraic Geometry, Cambridge University Press, 1953. A description of the condition of the books. Ex Libris a school, Mount Saint School, Scholastica College Library. I don't know that it's signed, but someone's kind of scribbled in the name. William Dallas Douglas Hodge. So Hodge is famous for the Hodge duel. So Hodge and de Rham come up making for holonomy and monogamy, which are these key things. So when Langlands is talking about sheaves and geometry and the account of the transference from algebra to geometry and back, makes the point, it's like, yeah, well, when things are really simple, then it's simple because it's just like a square, a lattice, and a box. But as soon as there's a twist or torsion, it's lost. And so cohomology and for homologies and cohomologies are when it's okay. Those the transfer results are bidirectional and they go back and forth. And then the usual account, though, is any count of even a right angle breaks that. So then there's an idea about the regulus, which is a shape, for example, in 2 dimensions that can be formed only of straight lines. And so then if you can imagine bending that about not a crease or a kink, but just like so that it still preserves that if through any piece of the paper there's a straight line that shoots through it and never leaves a sheet of paper. The regulus, and so you can imagine cones being made of these, or otherwise that a regulus would have 2 sides and congruency and complementarity. That what Langlands was describing is it's hard to relate the sheafs, the bundles and the sheafs of topology, which are like from Nelson's internal set theory, these partitions inside. That here for something like the Zolfray metric and if we're relating that to space-time, and then here for the Hodge dual and de Rham space, de Rham cohomology. That's the account from algebraic geometry that would need to be fulfilled by anybody talking about the geometric Langlands program and these kinds of things. Good day, gentle readers. That's today's talk. Quine to Scott, Fresnel and FitzGerald.